This presentation is about the monatomic elements in the periodic table, the noble gases in other words. I'm going to start with a brief introduction to the noble gases and a little bit about their discovery, and then I'm going to talk about something called London dispersion forces. So throughout this presentation, I'm going to give you a few quotes from this book here called Concerning the Nature of Things, and it's a book which contains 6 lectures delivered by Sir William Bragg at the Royal Institution in Christmas 1919. Now, I've read a bit of it, I've not read the whole thing. I find it really fascinating. I love books about science from a significant time ago. I think it's really interesting to see what people knew at certain points in time. Actually, our knowledge of chemistry has not changed that much since these lectures were delivered, so he gives a really nice in-depth explanation of things like atomic structure at a time when atomic structure had only just been discovered. It's a really fascinating book. I think he's got some nice things to say about the chemistry, so that's why I'm going to use some of these quotes throughout this presentation. So the noble gases were the last group of the periodic table to be discovered. If you think about what the noble gases actually are, it's easy to see why they weren't discovered until we had reasonably advanced techniques in chemistry. They are colourless, odourless gases, so distinguishing them from air is pretty difficult actually. I'm not going to go into the details of the discovery of each one. You might notice that helium, though, was discovered earlier than the rest. That's because helium, you might know that when radioactive substances decay, one of the ways in which they can decay is by emission of an alpha particle. An alpha particle is essentially a helium nucleus which very quickly picks up some electrons once it's ejected from the radioactive atom. So if you had a radioactive source that was an alpha emitter, around that radioactive source you would get a build-up of this gas helium. So that's why helium was discovered a little bit earlier than the rest of them. On the next slide, there's actually also a little bit more detail on the discovery of argon, which is a little bit more in-depth information. So I'll just quote you what William Bragg said about these gases. He said, "These substances have only the feeblest desire to join up with each other. They do not enter into combinations with atoms of other kinds. In other words, they do not form chemical compounds. We may call them unsociable atoms." So that's just re-emphasising what you would have already learned in National 5, that the noble gases do not form compounds. They are, in other words, completely unreactive. This slide's completely optional. It's about the discovery of argon. It might look a bit daunting. If you don't feel like reading it, don't worry, but if you do want to read it, then make sure you've done that first before you listen to the rest of this audio. So what this paragraph is essentially describing is the experiments done by Lord Rayleigh which led to the discovery of argon. So what he did was he prepared pure nitrogen through an experiment. So he caused a compound to break down, and he knew that the product of that decomposition was going to be pure nitrogen, and he measured the density of the nitrogen gas. He then compared the density of what he knew to be pure nitrogen with the density of a sample of air once he'd extracted all of the other known gases from it apart from nitrogen. What he noticed was that the density of this sample from the air, which should have in theory been pure nitrogen, would have been slightly more dense than the nitrogen, the pure nitrogen that had been made by a chemical reaction. From this, he knew that there must be something else in the air other than pure nitrogen, and I'm not sure exactly how, but he's obviously done some other kind of chemical processes or some calculations to work out the atomic mass of the other gas that must be present in this air. So we've said that the noble gases have a monatomic structure. That means they only exist as atoms on their own. They don't form chemical bonds as we have previously thought of chemical bonds, but they don't form ionic, covalent or metallic bonds. However, and again I'm going to quote from Bragg's book, "We must not suppose that these strange atoms cannot be made to associate together under any circumstances. It is possible to make them join together as a liquid, but only at extremely low temperatures." So, for example, the boiling point of helium is minus 272 degrees C. I've just got this little diagram on here as a reminder for you that the boiling point we conventionally think of as the temperature at which a liquid boils and turns into a gas, but of course that is the same. The boiling point is the same as the temperature at which, if we cooled a gas down, it would condense or liquefy and turn into a liquid. So, even though these are monatomic gases, they don't form chemical bonds. It's possible to join them together as a liquid. So what is holding the atoms together in the liquid and solid state? That's a question that we're going to look at over the next few slides. The fact that noble gases could condense and form liquids and even freeze to form solids was a puzzle for scientists. This is why. So in our understanding of atomic structure, we suppose that the outer shell of atoms contains negative electrons. The outer shells should repel each other, preventing atoms from coming together. So we remember, hopefully, that two negative charges will repel, just like the same poles of a magnet should repel each other. And when atoms or molecules in the gas state are moving fairly quickly, they do bounce off each other. So it's just like you try bringing two poles of a magnet together, there's a repulsive force. The atoms and molecules in the gas state bounce off each other a bit like snooker balls. And this is one of the assumptions in the ideal gas laws in physics, which you might learn about if you study physics. But what we have learned is that at slow speeds of approach, when we cool these gases down, the atoms may actually stick together. Otherwise, how can we form liquids? How can the noble gases form liquids at all? There must be some kind of attractive force which can form between atoms of the noble gases. These forces are known as London dispersion forces, and they're named after Fritz London, who was the originator of this theory of how atoms stick together. We've said that there must be some kind of force of attraction that can arise between the atoms of noble gases, and we've said that these forces are called London dispersion forces. In this slide, we're going to look at how these forces arise. What we've got to picture is we've got to picture the cloud of electrons, the electrons orbiting the nucleus of an atom as a cloud. And the electrons are moving round and round the nucleus. What happens is at a certain point in time, we might get a temporary uneven distribution of electrons that occurs in an atom. Now, I like to think about this as a wobble in the electron cloud, or you can think about it as the wobble of a jelly. So if we've got a jelly that wobbles, there'll be slightly more jelly on one side of the plate than on the other. A similar thing happens with these electrons. We get a temporary uneven distribution of electrons in our atom. Now, because electrons are charged, this then means that part of the atom which has more electrons becomes slightly negatively charged. The part of the atom which temporarily has less electrons becomes slightly positively charged. This separation of charges is called a dipole. So dipole is a word which just means a separation of charges. It means somewhere where we've got a positive and a negative together in a similar place but separate. Because it's temporary, it's called a temporary dipole. So this wobble in the electron cloud leads to a temporary dipole. The temporary dipole can then affect electrons in the neighbouring atom. So in this picture, we can see how the slightly negative part of a helium atom on the left might then repel the electrons in the helium atom on the right. That would then lead to the part of the helium atom on the right that's closest to the negative becoming positive, and those negative electrons are pushed away from the negative side of the dipole in the original atom. So the temporary dipole affects the electrons in the neighbouring atom, leading to an induced dipole. What we then have is we have a slightly negative bit next to a slightly positive bit. Opposites in chemistry attract, so the London dispersion forces are the electrostatic attraction between temporary dipoles and these induced dipoles. I just wanted to explain this diagram in a little bit more detail, just to explain how we talk about the symbols. So The little symbol that you can see in this diagram that looks a wee bit maybe like a tadpole or something, that's the Greek letter delta, the lowercase of the Greek letter delta. And so if we were talking about these symbols in chemistry, the one with a negative we would call delta negative or delta minus, and the delta sign with a plus we would call delta positive or delta plus. And the dotted line here is used to represent the London dispersion forces. So like we said in the previous slide, the London dispersion force is the force of attraction between the negative part of a temporary dipole and the positive part of an induced dipole, or vice versa. So London dispersion forces are an electrostatic attraction between negative electrically charged parts of the atom and positive electrically charged parts of the atom. We've said that London dispersion forces are the only forces which exist between the monatomic elements, or the noble gases. On the previous slide we also said that London dispersions were the only type of intermolecular forces that exist between molecular elements. In this slide we're going to look at the strength of London dispersion forces. So we know London dispersion forces must be relatively weak, at least compared to ionic, covalent or metallic bonds. We know they must be comparatively weak because the noble gases and molecular elements have very low melting and boiling points. An explanation for why these forces are so weak is because they are the result of these temporary dipoles, these temporary wobbles which are constantly changing. However, the strength of London dispersion forces is not the same for all atoms and molecules. The greater the number of electrons in an atom or molecule, the stronger the London dispersion forces. You can picture the jelly analogy again. If you imagine a really small jelly, you're only going to have a little wobble. So if you've got a small number of electrons, you're only going to have a little wobble in the electron cloud. If you're carrying a big, huge wobbly jelly on a plate, you're going to have a much bigger wobble. You would have a much greater, a much stronger temporary dipole in your molecule. So you can think about it a bit like that. A simpler way of looking at it in general is just to think about the fact that the larger the atom or molecule, the stronger the London dispersion forces. But the SQA prefer you to talk about the number of electrons in exam questions, so the key phrase to learn is this one, the third bullet point here. The greater the number of electrons in an atom or molecule, the stronger the London dispersion forces, and that's the one you want to use in your answers to questions because that's the explanation that the SQA prefer.